Hey everybody, today we are talking about aldehydes and ketones. So these two compounds are put together in this chapter because they are very similar in their reactivity. Specifically, both functional groups possess a carbonyl, a carbon double bonded to an oxygen. What is the difference? A ketone will be an internal carbonyl, internal to a carbon chain. So you'll notice that there are two carbons attached to each side of the carbonyl group on a ketone. An aldehyde will be at the end of a carbon chain. The aldehyde has to have a hydrogen on one side. The simplest aldehyde, formaldehyde down here, is used as a preservative. Acetone is the simplest ketone, and it's used in many solvents. You can see that found in hardware stores or in beauty supply places. Acetone is readily available to us, but the one that is readily available is usually lower in concentration. Now, ketones and aldehydes exist all around us. If you have ever made cookies, that vanilla flavor that you use to make chocolate chip cookies is vanillin, which is an aldehyde. And you can see all sorts of things. Even the progesterone and testosterone have ketones in them. Now, we know a lot of ways to make aldehydes and ketones. We're going to start here in section 3. We're not going to go through naming in section 2. We're just going to jump straight to their preparation. Now, this is a review. A lot of these reactions were in previous chapters. Just please note what's great about this. These images from the textbook is that they reference the section number that this reaction is in. So oxidation of primary alcohols. Notice that this carbon here, which we will call the alpha carbon, has two alpha hydrogens. Using PCC was the way that we oxidized this alpha carbon to an aldehyde. Another way to make aldehydes was with ozonolysis of alkenes, specifically if the alkene on each side, let's just call this carbon 1 and carbon 2, as long as each of those carbons had one hydrogen, then they would form aldehydes, right? And ozonolysis, O3, followed by dimethyl sulfide, is going to create two carbonyl compounds, one on each of those carbons. Hydroboration oxidation of terminal alkynes. Remember, in hydroboration oxidation, we are a concerted reaction, and so the boron gets inserted at the least sterically hindered carbon. And so for a terminal alkyne, the end position, or what I've highlighted there as carbon number 2, is going to be the least sterically hindered position, and so that is the one that gets the oxygen, and then the oxidation port converts an enol to a aldehyde. Now with our ketone preparation, again, review very similar ones that we had seen before, just going straight to the ketone. Oxidation of secondary alcohols. Again, we have an alpha carbon with one hydrogen. We can't use PCC on this one as readily. You can, but it's not as good. Sodium dichromate in acid solution, right? So this is a strong oxidizing agent. PCC would be the mild oxidizing agent. It can be used, but here we're just showing go big or go home. And it converts that alpha carbon to a ketone. Ozonolysis can also be done of alkenes. Tetrasubstituted alkenes will be cleaved to form ketones. So as long as all of those groups are carbon groups around that double bond, when it gets cleaved with ozonolysis, it will form a ketone. Ozonolysis will form ketones and aldehydes. There's only separated in your textbook here just to show you what is being prepared, aldehyde or ketone. But just note, ozonolysis can make a variety of aldehydes and ketones at the same time. Acid catalyzed hydration of terminal alkynes. Again, acid catalyzed hydration goes through a bridged intermediate with the mercuric sulfate, and therefore it is Markovnikov addition. And so water, or the oxygen, therefore gets placed on the more substituted center. It's not the sterically hindered center, it's the center that has the better carbocation characteristics, right? So oxygen gets put on the Markovnikov atom, which is carbon number 1 here, which is highlighted, and therefore we make an internal carbonyl and therefore a ketone. Friedel-Crafts acylation also made our ketones specifically on a benzene ring. Aromatic rings that are not too strongly deactivated will react with an acyl halide in the presence of a Lewis acid to produce the aryl ketone. Now remember, you can't use Friedel-Crafts acylation on something that it has a strong deactivating group, such as a nitro group. So there were some limitations with this reaction, but overall it's a good one to make a ketone, specifically an aryl ketone. All right, so the carbonyl carbon is electrophilic, right? If we think about not only induction, but actually resonance, right? There's resonance with that pi bond where the pi electrons can move up to be a lone pair on the oxygen, which creates an actual positive charge on the carbon. And induction as well, right? The bond itself is already polar. So resonance is the actual movement of the electrons from the pi bond. Induction is just the pull of the electron density. All of those are pulling towards oxygen, so oxygen gets the delta minus, and the carbon of the carbonyl is a delta plus. So that carbon of the carbonyl is going to be our electrophile in all of these reactions. We're going to spend a lot of time looking at this carbon. Something else that's very important about this carbon is that that carbon is sp2 hybridized. So it's trigonal planar. That means when the nucleophile attacks that electrophile and kicks up those lone pairs to break the bond, that new bond created by the nucleophile is actually creating an sp3 hybridized center, all right? And so that tetrahedral center could be racemic, right? If it is, please remember that a nucleophile could also attack from the bottom side, right? So when nucleophiles attack sp2 carbons, if the sp3 resulting carbon is chiral, we get racemic mixtures. So just be very careful with all of these reactions. Aldehydes are generally more reactive towards nucleophiles than ketones are. Two main reasons for that is the steric effects. Aldehydes, because one side is a very, very small hydrogen, aldehydes are less sterically hindered. All right, so we have a hydrogen over here, which is the smallest atom on the periodic table, and so therefore a terminal carbonyl, an aldehyde, is going to be one that is the least sterically hindered at that delta plus, at the electrophile. The other problem with ketones and why they are slightly less reactive, slightly slower at reacting than aldehydes, is the electronic effects. Carbons donate electron density, right? And so ketones have 2 electron donating groups, pushing some electron density towards that electrophile, trying to stabilize it. Aldehydes only have 1. Of those electron donating groups. So the delta plus on an aldehyde is much larger than the delta plus on a ketone. Thinking about nucleophiles that require acidic conditions, we will see basic or acidic conditions. Now, Grignard reactions are going to be some of the reactions that we study in this chapter. Let's just pull this guy apart a little bit. Me is a CH3. It's bonded to a magnesium and a bromine. Now remember, carbon to a magnesium is not technically a covalent bond. In reality, that bond right there is an ionic bond. So we can actually erase that, and carbon would have a negative charge on it. So this is a basic reaction. And what that basic reagent is going to do is do what nucleophiles do best and attack the carbon of the carbonyl. When it does that, we make a new carbon-carbon bond, and then water is there to protonate our oxygen of the carbonyl. Notice how first we have a nucleophilic attack, and then second we have a proton transfer. We will go more in depth into this reaction, obviously, with the preparation of a Grignard reagent and how do we make it, how do we use it, what can it react with throughout this chapter. But it's a really good first impression of a basic condition for these nucleophilic addition reactions, where we're adding something to the carbon-oxygen double bond, right? And that first step is a basic step, something that looks like a very strong base. Carbon with a minus charge does look like a very strong base indeed. Generally, a strong nucleophile means that the reaction is under basic conditions. Carbon minus, H minus, things like that. Under these basic conditions, all nucleophiles will react under the same general mechanism, all right? So nucleophile attacks the electrophile, specifically the carbon of the carbonyl, and then we do a proton transfer, all right? So if your nucleophile over the reaction arrow is a base, if it has a negative charge, or if it is something that is extremely basic, it will just do the nucleophilic attack first, followed by a proton transfer. Notice that the intermediate is negatively charged, indicating, again, basic conditions. Aldehydes and ketones can react with weaker nucleophiles under acidic conditions. And it's, again, a very similar mechanism. We'll be following these two mechanisms, the basic condition and the acidic condition, throughout the entire chapter. Now, the only difference between the acidic and the basic is the basic went nucleophile attacks first, and then the proton transfer. Acidic is opposite. Proton transfer first, because we're in an acid, then we attack with the nucleophile. Now, when that proton transfer happens, we are going to be attacking the oxygen, or the oxygen of the carbonyl is going to be attacking the acid, right? Because if the carbon of the carbonyl is the electrophile, that means that the oxygen is more nucleophilic, right? And that proton transfer actually makes the carbon of our carbonyl more electrophilic, more susceptible to a nucleophilic attack, because now that oxygen is positively charged. We are going to see a few of our wonderful atoms being our nucleophiles. Some of them are weak, some of them are strong. Right? So we're going to look at all 5 of these. We'll start with oxygens. Sulfurs are the exact same as oxygens, because remember, these are from the same family on the periodic table. So if something is from the same family, they tend to react the same way. And that's what we do see with oxygen and sulfur nucleophiles. Then we'll talk about nitrogens, and then hydrogens and carbons. As we move across this group, right, we are actually getting more electropositive, or what you can think about is less an electronegative, right? That's the same idea. And so what that means is that we are going to be more reactive as the nucleophile because those atoms do not like electrons, all right? So oxygens and sulfurs don't mind electrons. Nitrogens, they're less electronegative, so they do not care about keeping their electrons. Hydride, H minus, oh no, it wants to give that up. It wants to give that negative charge up. Same with carbon minuses. Okay,